Okay, to recap on the last lesson, we know that energy is released when there's a mass defect, and this mass defect times c squared is equal to the energy released. In the case of helium, due to the mass defect, we know it's 28.32 MeV per c squared, and it ends up being 28.32 MeV. This is energy released when a helium nucleus is made from its constituent nucleons. But obviously the bigger the nucleus, the more energy is released, so we have to compare them by talking about the energy per nucleon. This is a more interesting factor. So in the case of helium, it's going to be 7.1 MeV per nucleon. Most elements are around 8 MeV when they're made from their constituent nucleons. This brings us on to three definitions. The mass defect. This is the difference in the mass between before and after any nuclear reaction. So this mass defect is basically converted to energy, and this energy is also needed if you want to separate the nucleons again. So when the particles come together, they release energy. To pull them apart, you need to put energy in them to separate them. So it's any nuclear interaction. The binding energy. Now this is a bit like the mass defect, but it's not any nuclear interaction. This is the difference basically between the mass of the nucleus and the sum of the masses of its individual nucleons. Remember that mass and energy are equivalent. Another way of saying it is the energy required to separate the nucleus into its component nucleons or constituent nucleons. How is this different from the mass defect? Well, with the mass defect you could have two already large nucleons coming together. They would produce a larger nucleon and there will be a mass defect. The binding energy is this difference in mass or energy when the nucleus is formed from its separate constituent nucleons. And the most useful factor is not the total binding energy, but if we divide by the number of nucleons, this gives the binding energy per nucleon. So this is the total energy loss when a nucleus is made, or lost is released, per nucleon. In other words, it's the difference between the mass of the nucleus and the sum of the masses of its individual nucleons divided by the number of nucleons. You remember that helium had a binding energy per nucleon of 7.07. Lithium has a binding energy of 5.74. Iron has 8.79, and so on. Obviously, as the mass of the particle increases, the total binding energy increases. So we have to divide by the number of nucleons to find the binding energy per nucleon. So you notice that as we go from deuterium upwards, it's 1.12, 7.07, 5.74, 6.46, and so on, up to 8.779, which means to make these particles, you're releasing more and more energy. However, once you go past iron, it releases less energy than iron. So what this means, there's a tendency for the nuclei to, when they fuse, to form heavier, larger nucleons up until iron. After that, they would actually have to lose energy. You need energy to put them together. So the ones higher than iron are not likely to happen, because you would have to put energy in there to make them come together. That would be an endothermic interaction, and that's not likely to happen. So we have a graph. We graph this value of the binding energy per nucleon. It goes up very quickly, up to about iron, which is 56 here, and that's the highest point. So when the nuclei fuse together, they tend to go in this direction, forming larger and larger nuclei with a greater and greater binding energy per nucleon. However, it's not easy to get these larger nuclei to fuse together, because then you're actually going to end up with less energy than before. So you'd have to put energy in to make this happen. So whereas this process happens in this direction, it won't happen beyond here. However, it is possible to get uranium to go this way instead, the very heavy particles to move this way. So larger nuclei are much more have a greater tendency to split and release energy. Smaller nuclei have a greater tendency to fuse to release energy, always ending up in the 56 roughly, which is the iron value. So you need to annotate and draw showing the variation of nucleon number and the binding energy per nucleon. So you can see how it goes. It goes up to around 8 or 9 with iron, and then it goes down to about a little bit less than 8 for uranium. So this kind of curve, you need to be able to recognize it and be able to sketch it. Another way of looking at it is by inverting this graph, and you say that you can imagine a ball rolling down the hill. It will tend to roll in this direction towards iron. If it's here, it will tend to roll towards iron as well, because it needs to go to its lowest level of energy, its lowest potential energy in this sense. Here we have a past paper question from 2004. Use the following data to deduce that the binding energy per nucleon of the isotope helium-32 is 2.2 MeV. You're told that the nuclear mass of the helium isotope is 3.01603. The mass of the proton is this, the mass of the neutron is this, and 1 unit is this. So we have to find out how much do we have before and how much do we have afterwards. So the mass of the nucleons before. So you could try to do this now, and I will go through the solution. The mass of the nucleons before, we have, it's 3,2, which means we have 2 protons, so it's 2 lots of this value and 1 lots of this value. This gives a value of 3.02323 unified atomic mass units before the nucleus is created. Afterwards, we are told that the mass is 3.01603, which is different from this. Some energy is lost. So what is the mass defect and what is the mass that's lost? Is equal to 0.0072 unified atomic mass units. Now we're told that 1 unified atomic mass unit is equal to 931.5 MeV per c squared, and that works out to be 6.7 MeV per c squared. What is this in terms of energy? E is equal to this mass c squared. The c squared cancels with the c to the minus 2. So we have E is equal to mc squared, and you're going to end up with a value of 6.7 divided by 3 gives 2.2 MeV. Nuclear fission and nuclear fusion. Sometimes they ask this. Fission is when large nuclei split to make smaller nuclei and release energy and become more stable. Nuclear fusion is when small nuclei join together when they fuse to make larger nuclei, and this releases energy. In other words, they become more stable. So you have to describe this graph and use it to account for the processes of fission and fusion. Now, the greater the binding energy per nucleon, the more tightly bound the nucleus is, the more energy it is able to release. Remember, fission is splitting nuclei. Fusion is joining nuclei together. So this is the most tightly bound nucleus, iron. Now, fission is when this releases energy. In other words, has to go to the highest mass defect, the highest binding energy per nucleon, has to go in this direction. So this will be fission. On the other hand, these tend to fuse to release energy. And here we have another graph. So fusion tends to go in this direction, fission in this direction, on either side of iron. And this is the example I mentioned before. Imagine a ball which rolls down. It will tend to go to towards iron, and it's not going to go uphill. It will end up here. This is the most stable. Where do we get these nuclei being produced? These basically happen in stars. And when we have large nuclei of uranium and so on, they will tend to split. They will tend to fission and go towards iron. State that nuclear fusion is the main source of the sun's energy. So the sun's energy from nuclear fusion is not by combustion, even though we say it's a hydrogen burning star, the sun for example. It's not burning, it's not combustion, it's nuclear fusion. We have heavy hydrogen nuclei fused together and they release lots of energy, this binding energy. The total mass is going to be less than the sum of the separate masses. So some mass disappears and this is the mass defect. This is converted to energy and this basically powers the sun.